Well, hey there, folks. Welcome to the Roundup. We're a Cowboy State Daily podcast that focuses on interesting people in the Cowboy State. I have to say, just as a disclaimer, the gentleman we're going to interview today, he doesn't live in the Cowboy State, but the work that he did in the Cowboy State has revolutionized, and I am not understating this, has revolutionized medicine, biomedical research, and affects each of us in our everyday lives. So I am so thrilled to be able to introduce Hudson Freeze, Dr. Hudson Freeze. Hud Freeze spent some very formative time in Yellowstone National Park here in 1966. And he's got some amazing stories to tell. But first, I just want to say, Hud, thank you so much for being on the podcast today. You and I have a real interesting and great connection as to how we met. But good day, Hud. We're so glad to have you here.
And Wendy, it's so good to be on your program here, and I'm glad that I can be the New Year's baby.
You are the New Year's baby. You're ringing in the new year with us, which is fantastic. I have to, a little bit of backstory here. So my music partner, my life partner, Dan Miller, Dan and Hud grew up 2 blocks from each other in the tiny town of Garrett, Indiana. And they then reconnected in California, and they were great friends and just bummed around Southern California for a while, right? That sound about correct?
Yeah.
While Hud was getting his doctorate and working on all the things that have led him to his career, Dan was being an actor, and he was taking acting, he was working there. So the two of you have this great connection, and I got to meet Hud in person a few years ago. The work, Hud, that you have done, has absolutely changed lives and has ripple effects. So Hud, tell me how you got from Indiana to Yellowstone National Park, for starters, and how that all came about.
It was a blessing. It was a stroke of luck, that's for sure. So I was an undergraduate college student at Indiana University, and I was one of the students in microbiology. It was called bacteriology at the time. And, I wanted to do some research. And so my advisor said, you need to go down and see Dr. Brock. And I had heard Brock give a lecture before, and I talked to him, and he says, well, we're not working on that stuff right now, but what we're doing is we're going to go to Yellowstone National Park. Would you like to come? It's sort of like, we're taking the first trip to Mars. You want to be on the rocket ship?
Absolutely.
And I thought, my gosh, I've never been out of Indiana except to go, a few miles that way. And I might actually get to see mountains and hot springs.
Yeah.
I thought, what could be better? I've not been out of Indiana. Let's give it a whirl. And the way this got connected is Tom was on a trip to the West Coast, and then he went through Yellowstone and saw all these beautiful colored hot springs. And you knew the temperature was really high, boiling water in some cases. But there were all these colored things around there. Well, what was that? He thought it was probably bacteria and algae that were growing in the hot springs. And what was amazing is nobody thought that you could live above 50 degrees centigrade. And that's, about like 130, that's somewhere around there, kind of dishwasher temperature, that you could not even go close to that. And he said, no, it's not true. I think you can live any place there's water, even if it's boiling. And so this was his idea, and he said, come along and we'll see what we can discover.
So that's how you got to Yellowstone. And you get there and you're actually doing the digging in the water stuff. You're pulling samples and things like that. At what point did you discover that you found something that could be revolutionary?
Oh gosh, there was none of that. I mean, that's what was really important about basic science. I mean, you do it because it's, well, gosh, that's funny. Yeah, you shouldn't be able to live, or how do you do that? So it's that curiosity that brings you in to start with. And so I was an undergraduate student. I was curious. So, all right. And we weren't sure that you could actually grow this stuff in the laboratory. So it took about a month after I got back to look into trying to make the bacteria that we thought were there and we could sort of see them, get them to grow in the lab. So I had a bunch of different experiments going. I picked up a tube that had growth medium in it that I added a couple of drops of spring water to. And I would swirl it like that. Nothing in there to see, right? Next day, no. Next day, no. Wait, I'll come back tomorrow. There's all this stuff floating around in there. And this is at 70 degrees centigrade. That is about, I don't know, 165, 170 degrees Fahrenheit.
Very, very hot.
Real hot. And so I thought, well, let's take a look and see if it's really bacteria. So I take a little pipette, which is a little tube, put it in there, went over to the slide, put it under the microscope. It's the honest truth. I still get goosebumps when I think back to that moment. So I'm focusing the microscope. I see all these worms crawling around, all these microscopic worms. And I am just thrilled. But there's no application. There is no need for having this other than, gee, that's funny. How do they grow? So it turned out that, I published a couple of papers and tried to understand how they survived. But that was about it. And there was not a big use. I think at one point, Procter and Gamble came to us and thought maybe they could add this stuff into Tide and that it would make clothes cleaner at higher temperatures.
Really? Oh my
Yeah, I
gosh.
mean, that was the only application.
That's all that was. Okay. All right. So at what point did you was the connection made that, wait a minute, this actually is the key to everything?
So I didn't make that connection. The guy who made the connection is named Kerry Mullis. And he probably on an LSD trip, he's kind of an unusual character, came up with the idea. And so what's involved is DNA hangs together as two strands. But if you raise the temperature, you can make them melt apart.
No kidding.
Yeah. And you lower the temperature and they come back together. So if you take the temperature up and you provide an enzyme that will actually replicate the DNA, and that had been known for a long time, you can make two identical copies of that, right? And then, if you take the temperature down, and then the strands would come back together, and then they would come apart. The problem was if you added this enzyme every time you did this, because the enzyme won't work at high temperatures where the DNA melts. So every time you wanted to go in and go from 2 to 4 to 16 to 32 to 64, every time you do that, you'd have to add more enzyme.
So you're diluting it, right?
Well, it's not only that, because you inactivate the enzyme from the previous round. So you have to add more so that you've got the driver for it.
Okay.
So what happened is he had this idea that came from, I think maybe somebody else too. He says, well, what if we use an enzyme from this organism that grows in Yellowstone? It's very happy up at that temperature. You don't have to add it. You add it once and you forget it, and you take the temperature up and bring it down. Bringing the temperature down doesn't hurt it. Take it up again. And so you could make one DNA molecule, any kind of DNA molecule, into 1 billion copies. 1 billion.
That's monumental, because then the applications for it are everywhere. They're for research, but they're also for example. I mean, I'm a true crime aficionado, and so you hear about DNA advances in DNA research, and you can't, at one time in the 1970s, DNA meant nothing, and you can't find out. You if you lose this sample, you're done. But with this new research, with this new discovery, they're like, oh, so we can replicate this. And now we can solve crimes that happened 30, 40, 50 years ago.
And that's how many accused criminals who are serving time get off, because you can show their DNA does not match the DNA from the crime. So
Exactly.
it's been a big help.
So that's just one application. There's so many others. Vaccines, HUD, are you can research them, you can create vaccines because of this enzyme that was found in Yellowstone. Tell us how that works.
Well, anytime you have a piece of DNA, it almost doesn't matter, even if, as I said, if you have one copy of DNA, you can convert that into 1 billion copies, which then allows you to look at the sequence. Now, I'll get a little bit techie here. The sequence determines what the gene is making. And there are 4 bases: A, T, G, and C. A pairs with T, G with C. And so you're able to, when you melt these apart and provide the raw materials and the polymerase, it knows how to stitch it together and make exact copies. So you can multiply it that way. So even in the tiniest amount of DNA, you can select a piece and say, okay. And we knew how to find the sequence. We didn't know how to amplify it. But you can pick that and you can see if there is a mutation in that gene. You can tell if there's a variant of some sort that shouldn't be there. And maybe that's responsible for some kids being sick.
Which is where you come in and where you took off and changed the trajectory of your research. Hud, tell us about your research, because the research that you're doing, now that you can amplify and view and study the mutations in genes, you are able then to identify these diseases in children and help them. Tell us about your work. And your work is at Sanford Burnham Prebys, and that's in
That's,
California.
that's right.
And tell us about what you're doing with kids there.
Well, so I'm a basic scientist. I'm a lab rat. I'm not a physician, but I had my sister is developmentally disabled. And, I was and still am very close to her. So, I have a certain affinity for kids that have problems. And I have been doing some work involving slime molds, if you can imagine. So I did some work with that. But then one of my friends sent me some cells from a patient who had some disorder in these things that we study. We didn't know what it was. And I looked at that and I said, well, I think I can make a difference by applying some of my old work to this. So we were able to, in a few cases, actually end up treating some patients with a simple sugar. I mean, not just any sugar, but a specific sugar that we understood the fundamental basis of and the biochemistry for. And then we were able to see that the gene that would be important for making that had a mistake in it. And so that one wasn't good enough to power things through. But if we added, in some cases, not all, if we added a certain sugar to the diet of these patients.
No kidding.
Yeah, I mean, it was really wonderful. And so, as a basic scientist with no medical training, I was able to get in and have a lot of relationships with physicians and with families. And of course, having the relationships with families was a lot like being at home, right? I mean, all these kids were around, and I feel very comfortable with that. And then knowing that I might be able to help them, even if it's just for a diagnosis. That's really important to the parents. We never found out what was wrong with my sister. And maybe it doesn't cure it, but it gives you some knowledge that somebody out there knows besides just the suffering you're doing with your own family.
And of course, one of the things that you have learned and that you've experienced is that even though right now you can't cure it, the advances that have been made since 1966 at Yellowstone National Park have gone leaps and bounds. And so someday, with this basic research, maybe there can be a cure for these.
Oh, I think so. In fact, I would say every biotech company, every university, every one who does anything in biology is using PCR.
And so PCR is
the polymerase chain reaction
okay.
that this guy, Kerry Mullis, developed, coming from, but the critical ingredient was adding the Thermus aquaticus. That's what we named this thing. Polymerase. So it's called TAC, T-A-Q. TAC polymerase.
And I have to say, you've got it there with you. You received a very special award for your you got to hold up. You got to hold it up because it's so cool. So, had you received the Golden Goose Award? I love that, the Golden Goose Award for your work on Thomas aquaticus, or Thomas Thermus aquaticus.
Thermus aquaticus.
Yes.
Yeah, and the basis of the award is here is basic science that people might ridicule. Why are you going to hot springs and trudging around and doing things? That has no practical application. Come on. What are you doing? But you wait a little while. You get the right things together, and now suddenly it changes the world.
And it has changed the world.
Yeah, it really has.
And so tell us other ways in which this work this has changed the world, because, I mean, we've talked about criminals, we've talked about vaccines, we've talked about childhood diseases. What are some other ways that PCR is being used in science and in practical applications every day?
Yeah, I think if anybody has ever gone to 23andMe, okay, they use PCR to take a little bit of your DNA, amplify it, and then see what your origins might be. But they also will do some very targeted things where if you have let's say a mutation that is in a rare disease, but still it's a very common mutation in that disease, they'll tell you about it. And the reason that's important is because if you have two people who would have mutations in that same gene, their children might have either a 25 or 50% chance of having a disease that would come from that. So prenatally, you can decide, well, is this a good match? Should we do in vitro fertilization if you're oriented that way? So you can decide based on PCR. And of course, that then leads into 23andMe to what is your ancestry? Where did you come from? What was interesting was my wife had me do this. And there's nothing too surprising in our backgrounds, except they said, you carry this mutation. And it's one of the diseases that I study. But you need to have two of those mutations in order to be sick. So I had one of them. And I thought, oh my God, what if my sister has this disease that I work on? We checked her DNA and she doesn't have it. But again, you realize that sometimes if you do this, you'll have a little bit of a warning if you need it. If you don't need it, it doesn't matter. Within the Jewish population, there's a couple of disorders that are very common. And so typically, the Eastern European Jews will have a set of disorders that come along. And, because they stay in small communities and get married to each other. And so, you can have that sort of founder effect of these things. And, at one point in over the last 5 or 10,000 years or something, it may have had an advantage. Maybe it prevented you from getting a disease. But the cost of that was that you also had sick kids. But evolution weighs and says, well, okay, it's worth the risk. We'll keep it around.
Wow. I
Yeah.
want to go ahead.
Nope, that's it.
So I want to transition just slightly and segue into speaking of sick kids. You were recently named the Distinguished Endowed Chair of the William W. Rue Foundation or Endowment.
Yeah.
And and this is an amazing story as to how this came about. And this endowment funded your research into these childhood diseases. But the story, I think, HUD, is just it's very, very touching. And again, this is practical application of science that we all on this, lay level don't think about. We don't think about all the research that goes into these things until we have a sick child, until we have a child with a genetic mutation in their blood, which I discovered last year with my daughter, who had a major health issue last year. And long story, but found out that I was a carrier for the genetic mutation. I
Uh-huh.
didn't know it until afterwards, but it
Yeah.
caused her a year's worth of life-threatening illness. These sorts of things and these sorts of discoveries don't always come at the right time, but when they do come, when these discoveries do come, they can make a difference in the future. So tell us about Rocket, because I love this story. This is a fantastic story about Rocket.
And this is all um, blessing or luck, or call it what you will. So it was now right around Christmas, about 18 years ago. Um, we had been sent some cells from a patient, and we hadn't analyzed them yet. And the dad wrote to me, and he says, well, as a Christmas present, you think you could do the analysis and see if this is what we think my child has? Well, there's one version of this that's treatable. There's another version of a different gene that's not treatable. And we did the analysis and told him, I said, well, it's not the treatable kind. Okay. Well, my mother and I would like to come down and see you, the grandmother. And I said, well, I don't have much to offer you, but you're welcome to come down and we'll talk. So the grandmother, Dinah Rue, comes down along with her son, Taylor. And Taylor says, well, is there any treatment? I said, no, there isn't. And Dinah, very quickly, elegant lady, says, well, what's the biggest obstacle in the field right now? So I told her a little bit about what that is in terms of diagnosis. And she said, well, could you do something about that? I said, yeah. She said, well, how much would it cost to get that going? And I said, oh, $100,000.
Okay.
Okay. Well, I'll talk to my husband about it, but I think we can manage that. So that happens. And every year since then, they've given us between $125,000 and $250,000 to carry on our work in the lab on these disorders. And in doing that, they realized, of course, that this should be done in perpetuity. So they created this chair. They made a really quite substantial donation to the institute, in my name, in creating this chair. And it even says, and I have trouble with this, honoring Hudson Freeze. So, and there's a chair that has all this engraved on it.
An
But
actual physical chair.
there's a physical chair. It's not just a figment of your imagination. So anyway, what happens is that now the proceeds from that, the interest, then goes to my lab or whoever my successor will be, and they can carry on work in Rocket's name, in Bill's name. and they kind of ensure that he's going to be around for a long time. And what's been interesting, and again, you have no way of knowing how this is going to come out. Early on, the family held a fundraiser for us at the old MGM studios. And it's because the dad is in the business, and one of mom's brothers is in the music business. And so we got autographed guitars like, from Trent Reznor of Nine Inch Nails.
Cool.
We had a coat that Madonna wore. We had autographed books and things like this. And so, we had that kind of a fundraiser. It was, really great. But it turned out that mom's side of the family is enormously prolific. Her sister Liberty is a famous model in London who then moved to the US and is now married to Jimmy Ivey, who with Dr. Dre was Apple Music.
Oh my goodness.
And so she said one time, well, Jimmy wants to throw a birthday party for me. She said, I don't need presents. How about they give it to the Rocket Fund? Is that all right? I said, yeah.
Yeah.
Good. And one of mom's other sibs is named Atticus Ross. And Atticus is Trent Reznor's creative partner in Nine Inch Nails and the music for the Social Network and all these other things. So suddenly I fell into this group of people who are not only famous, but they also have an immediate connection to all of this. And you could have never predicted that. And that's not why you do the work.
No, it's not. But it enriches your life.
Amen.
And then enriches the lives of the people who you touch. And Hud, you have the work that you have done and that you've contributed to, and not on your own, but in so many ways collaborated with people to create these amazing miracles and diagnoses and advance the work of science. Hud, it's just phenomenal. And it all started in Yellowstone National Park.
Yes, it did. That was my first blessing.
Well, it's been a blessing to so many then because of that, Hud. Thank you for explaining that in ways that us lay people that are not scientists can understand, and for the work that you're doing. Is there a place that we can go to find out more information about the work that you're doing and the work that your colleagues and your peers are doing for this continuing research?
You can go to our institute, which is Sanford Burnham Prebys Medical Discovery Institute. And there is a page there that refers back to our work, and there's information about the Rocket Fund. There is also a family group that is very, very active for covering all of these disorders. Now I was involved in the first discovery of one of these things back in about 1980, but there are now 200 of these diseases, 200 of them. And so there is a family group that is trying to at least serve all the families. You can't touch them all, but they're called CDG Care.
Okay.
And CDG stands for Congenital Disorders of Glycosylation. But that family group has just been awarded a 5-year grant from the Chan Zuckerberg Initiative so that they can go out and make these disorders better known to physicians, to families, to serve as a resource for people to come in and, really benefit from what we know scientifically and medically.
That's so amazing. What are you working on next, Hud? What's your next project that you're working on?
Well, we've got several. We have about 3 new diseases that we've discovered, working their way through the system to prove that they're really diseases. And there was another one that we've been working on for a while called Saul-Wilson syndrome. And that's a kind of dwarfism. And it's made, if you can believe this, from one change in just one of the genes, not in 2, not in both copies, but in one. And we're trying to figure out the basis of that. And we use patient cells to then differentiate them into things that would be giving rise to bones because their bones don't grow. So maybe if we
Right.
can understand that, we can understand it better.
Wow.
And a bunch of other things that are more basic science. So I keep straddling between the two ends.
You are busy and you are just creating and collaborating and making a difference in so many lives. Hud Freeze, thank you. Thank you so much for being on the show today, for kicking off our new year and for all the work that you're doing. I have to ask one more question. And it there was a movie made by with Harrison Ford and Brendan Fraser in it. And I want people to know how the movie Extraordinary Measures links to you and to your work.
Okay. So there's a couple clips out of the movie that I use in some of my lectures because Harrison Ford had just the right words. So I had worked in about 1980, 81 for a guy named Stuart Kornfeld, who was in Washington University in St. Louis. And we were working on how enzymes find their way to the right place in a cell. And what was involved was called mannose 6 phosphate. And that is a little thing that you put onto a sugar chain on a protein to direct it out this way. And I do get Ford to say, mannose 6 phosphate. It's just really great. So anyway, I knew the guy that he played. And, you know, that was in the same lab as I had been in. And so actually I wrote to Ford and I said, you did a great job of doing this. Doing this part because I know the guy, you hit it right on the money. I said, could we use your picture from that to advertise a scientific meeting? And 2 days later he answered and he said yes. So that was good, but the whole story was quite accurate, and the movie Extraordinary Measures gets played in a lot of rare disease settings. So
Okay.
Okay.
But the movie then is working, it focuses on the same work that you've been doing all of these years. And
Somewhat
yes,
similar. Yeah. I mean, there's an overlap in that, and not all of it is exactly what I'm doing, but
yeah.
it's in the same general area, and we use the same kind of approaches. And I use mannose 6 phosphate oftentimes because it turns out to be an ingredient that's important for me.
Really? So, okay. All right. I know that that's something that has come up in conversation before. I'm like, I know that this movie has something to do with your research. And so I wanted to check that out and have people, if they're interested in learning more about this process and they want to hear a story about it, then this is a story about how genetic research and the genetic work that you're doing, how it impacts people's lives.
That's right.
Absolutely. Hud, this has been so interesting. Thank you for being a part of our the Roundup family now, and also for continuing to do the work that you do. And we hope to see you very soon. So thanks for being a part of this today.
Wendy, thanks for the privilege and the invitation. And Happy New Year.
Happy New Year to you as well, and Happy New Year to all of you. 2025 is going to be a great year, and we're glad to kick it off on the Roundup with Hud Freeze and this really important work that he's doing. Folks, have a wonderful week. We will see you next week right here on the Roundup.